It's the summer of 1950. Los Alamos, New Mexico. A group of physicists are eating lunch. These aren't just any physicists. These are the people who split the atom, who rewired what humanity is capable of. They're talking about something ridiculous. A cartoon in the New Yorker showing aliens stealing New York's trash cans. The conversation shifts. Someone jokes about UFOs, then about faster-than-light travel. Then, slowly, it drifts into something bigger. If the universe is as vast, this old, where is everyone? And then Enrico Fermi, Nobel Prize winner, architect of the nuclear age, one of the sharpest minds of the 20th century, puts down his fork and asks a question that nobody in that room could answer. Where is everybody? 4 words. That's all. 75 years later, we still don't have an answer. Let me give you the numbers, because without them, the question doesn't fully land. The observable universe contains an estimated 2 trillion galaxies. Our own galaxy, the Milky Way, holds somewhere between 100 and 400 billion stars. And based on data from NASA's Kepler Space Telescope, we now know that most of those stars are planets. Rocky, Earth-sized planets in habitable zones. The right distance from their star, the right temperature for liquid water, are not rare exceptions. They're common. Run the math, and you get billions of potentially habitable worlds in our galaxy alone. The universe has existed for 13.8 billion years. Our solar system is only 4.6 billion years old, meaning there are civilizations that, if they exist, had a multi-billion-year head start on us. If just a fraction of those worlds develop life, and a fraction of that developed intelligence, the galaxy should be crowded. We should be picking up signals. We should be seeing megastructures, probes, something. Instead, silence. Complete, unbroken, total silence. And here's the part that keeps certain scientists awake at night. That silence is not neutral. It's data. It's telling us something. We just don't know what. This is the Fermi Paradox. Not a paradox in a technical sense. It's not a logical contradiction. It's something worse. The gap between what the math predicts and what reality shows us. A question with no comfortable answer. And depending on which answer turns out to be true, the implications for humanity range from profound to terrifying. We didn't just sit with a question. We went looking. In 1960, an astronomer named Frank Drake pointed a radio telescope at 2 nearby sun-like stars and listened. He called it Project Ozma. He heard nothing, but the experiment planted a seed, and within a few years, the search for extraterrestrial intelligence, SETI, was born as a formal scientific discipline. The logic was straightforward. If a civilization wanted to make contact across interstellar distances, radio waves were the obvious choice. They travel at the speed of light. They're cheap to produce, and they pass through the galaxy with minimal distortion. If we were broadcasting, maybe others were too. For decades, telescopes across the world scanned the sky. Millions of frequency channels, billions of data points, countless hours of human and machine analysis. And then on August 15, 1977, something happened. At Ohio State University's Big Ear Radio Telescope, during a routine SETI survey, the equipment recorded a signal. It was narrowband, exactly the kind of tight, focused transmission that would suggest artificial origin. It appeared to come from the direction of the constellation Sagittarius. It rose and fell in a smooth, bell-shaped curve over 72 seconds, precisely matching how a signal from a fixed point in space would look as Earth rotated to the telescope's field of view. A few days later, astronomer Jerry Emmon was reviewing the printout. He circled the signal's intensity readout, 6 EQJ5, and in the margin wrote one word: wow. It remains nearly 5 decades later, the most intriguing signal SETI has ever recorded. Here's what makes it genuinely strange. It was never detected again. Dozens of follow-up observations pointed at the same patch of sky. Nothing. The signal came once, matched every criterion for what we'd expect from an artificial transmission, and then vanished. As recently as August 2025, researchers from the Arecibo WOW project published a new analysis, the most detailed examination of the original data ever conducted, and their findings suggest it was not caused by terrestrial radio interference, though they propose it might have been a naturally occurring astrophysical phenomenon, possibly a rare interaction involving interstellar hydrogen clouds. The lead researcher himself acknowledged, "Our results don't solve the mystery of the WOW signal. It remains officially unexplained. Not confirmed alien. Not confirmed natural. Just open." Now, here's the part of SETI's story that most people don't fully grasp, and it reframes the entire silence problem. Everything we've ever broadcast, every radio signal, every television transmission, every radar pulse since the 1920s is expanding outward from Earth as a growing sphere of electromagnetic radiation. Scientists call it our radio bubble, and it sounds impressive until you look at the map. That bubble is roughly 100 light years across. The Milky Way is 100,000 light years across. We have reached, in terms of radio silence, 1,000th of our own galaxy's diameter. The nearest star system, Alpha Centauri, at 4.24 light years away, only received our earliest signals within the last century. But it gets worse. The laws of physics aren't on our side. Radio signals obey what's called the inverse square law. Their intensity drops with the square of the distance. A signal that's already faint at 10 light years becomes essentially indistinguishable from natural cosmic background noise at 100. Our most powerful intentional transmissions would be nearly impossible to detect with current technology from even a few hundred light years away. We are, in a sense, whispering into a storm and wondering why no one calls back. And that raises a question we should sit with. What if others are doing exactly the same thing? What if the galaxy is full of civilizations, each confined to their own tiny radio bubble, each too far away, each signal too faint? All of them listening, none of them hearing. It's a comforting thought, but it doesn't fully hold up, because SETI isn't just listening for radio. Modern searches look for laser pulses, for anomalous infrared radiation, for what scientists call technosignatures, any detectable sign that technology exists somewhere. And in April 2025, something genuinely remarkable happened. A team at the University of Cambridge, using the James Webb Space Telescope, announced what they call the strongest evidence yet of a possible biosignature on an exoplanet called K2-18b, a world 124 light years from Earth. Using JWST, astronomers detected the chemical fingerprints of dimethyl sulfide and dimethyl disulfide in the planet's atmosphere, molecules that on Earth are produced exclusively by living organisms, primarily marine phytoplankton. The reaction from the scientific community was immediate and divided. A subsequent NASA-led analysis confirmed K2-18b's water-rich atmosphere, but found no conclusive evidence of DMS, noting that the signal sits well below the 5 sigma threshold required for a definitive scientific claim. Other researchers argue the data could equally be explained by non-biological chemistry, or even instrumental noise. The lead skeptic put it plainly, "Finding life beyond Earth is the ultimate goal of our field, but we need robust proof, not excitement-driven assumptions." This is where we are in 2025. We have a telescope powerful enough to analyze the atmosphere of a planet 124 light years away. We have a signal from 1977 that still hasn't been explained. We have billions of potentially habitable worlds and 0 confirmed contact. The universe is not giving us easy answers. It's giving us better questions. And the questions get darker from here. Let's start with the most hopeful explanation. And it goes like this. Maybe the universe isn't empty because something is stopping civilizations from emerging. Maybe it's empty because the conditions required to build a civilization like ours are so specific, so improbable, so reliant on a chain of accidents that spans billions of years, that we genuinely might be alone. This is known as the rare earth hypothesis. It was formalized in 2000 by paleontologist Peter Ward and astronomer Donald Brownlee in a book of the same name. And at its core, it makes a deceptively simple argument. Microbial life might be everywhere, but complex, intelligent life? That might require something close to a miracle. Start with where you are in the galaxy. Not all regions of the Milky Way are equal. The galactic center is a violent neighborhood, dense with radiation, supernovae, and gravitational chaos. The outer edges of the galaxy don't have enough heavy elements, iron, silicon, and carbon, to build rocky planets in the first place. There's a narrow ring, roughly where our solar system sits, sometimes called a galactic habitable zone, where the conditions are calm enough and the chemistry rich enough For complex life to potentially take hold, we happen to be in it. That's not guaranteed. Then there's the star itself. Our sun is unusually stable. Many stars flare violently, blasting their inner planets with radiation that would strip atmospheres and sterilize surfaces. Red dwarf stars, which are by far the most common type in the galaxy, are particularly prone to this. Our sun, a mid-sized yellow star with billions of years of steady output, is actually relatively rare. Then the planet. Earth's size is almost exactly right. Massive enough to hold a thick atmosphere and sustain geological activity. Not so massive that it collapses into a gas giant. It has a global magnetic field, generated by its rotating liquid iron core, which deflects a stream of charged particles from the sun that would otherwise erode the atmosphere over millions of years. Without that magnetic field, Earth might look more like Mars, a cold, airless, dead world that once had oceans and lost them. Then there's plate tectonics, the slow recycling of Earth's crust that regulates carbon levels, renews nutrients, and stabilizes the climate over geological time. Earth is, as far as we know, unusual among rocky planets in having sustained active plate tectonics throughout its history. And then there's the moon. Our moon is enormous relative to Earth, about a quarter of our planet's diameter, and formed from a collision so improbable that planetary scientists still debate its exact mechanics. What the moon does is stabilize Earth's axial tilt. Without it, our planet's axis would wobble chaotically over millions of years, swinging between extreme climate states that would likely prevent the long, stable evolutionary periods that produce complex life. Mars, which lacks a large moon, has experienced exactly that kind of axial chaos. And finally, Jupiter, the largest planet in our solar system, acts as a kind of gravitational shield. Its enormous mass deflects or captures a significant portion of comets and asteroids that would otherwise rain down on the inner solar system. Without Jupiter, Earth would likely face far more frequent extinction-level impact events. It's worth noting here that some researchers dispute exactly how effective Jupiter's shielding role is, and there are simulations suggesting it may, in some configurations, also redirect debris toward Earth. The science here is genuinely contested. But the broader point stands: the architecture of our solar system, with large gas giants in the outer reaches and small rocky planets inside, appears to be relatively uncommon among the planetary systems we've observed. Now step back and look at the full list. Galactic location, stellar type, planetary size, magnetic field, plate tectonics, a stabilizing moon, a protective giant neighbor. Each factor alone might be moderately common, but the probability of all of them occurring together, on the same planet, in the same window of time, may be extraordinarily small. The rare Earth hypothesis doesn't say life is impossible elsewhere. It says that the conditions required for life to survive long enough, and in stable enough conditions, to develop something as metabolically expensive and evolutionarily unlikely as a large brain, may be the exception, not the rule. And if that's true, then the silence isn't mystery at all. It's exactly what we should expect. But here's where the comfort of that explanation runs out, because the rare Earth hypothesis, as reassuring as it sounds, doesn't actually solve the paradox. It reduces the expected number of civilizations. It doesn't eliminate them, even with every factor stacked against it. In a galaxy of hundreds of billions of stars, the math still allows for some civilizations, perhaps dozens, perhaps hundreds, to have emerged over the last several billion years. And if any one of them had survived long enough, grown powerful enough, expanded far enough, we should see them. We don't, which means something else must be at work. Something that doesn't just make intelligent life rare, but stops it from persisting. That something has a name. In 1998, an economist named Robin Hanson wrote a short paper that reframed the entire question. He wasn't an astronomer. He wasn't a biologist. He was someone who thought carefully about probability. And what he noticed was this: if the expected number of visible civilizations is high, and the observed number is zero, then something in between those two realities must be filtering them out. He called it the Great Filter. The logic is elegant and brutal. Between the formation of a rocky planet and the emergence of a galaxy-spanning civilization, there are many steps. The origin of life, the jump from simple to complex cells, the emergence of multicellular organisms, the development of intelligence, the invention of technology, and finally, the leap into space. The great filter is the idea that at least one of these steps is almost impossibly difficult, a step so hard that virtually nothing makes it through. The question, and this is where things get uncomfortable, is where that filter sits. There are two possibilities. The first possibility, the filter is behind us. What if the hardest step wasn't building a rocket or avoiding a nuclear war, but something that happened billions of years ago, quietly in the chemistry of the early Earth? The origin of life itself is still not fully understood. We don't know exactly how non-living chemistry crossed the threshold into self-replicating molecules. It happened at least once on this planet. Whether it was an inevitable consequence of the right chemistry or a staggering accident is still an open question in science. More striking is the gap between simple and complex life. For roughly 3 billion years after life first appeared on Earth, nothing more complicated than bacteria existed. The jump to eukaryotic cells, cells with a proper nucleus, appears to have happened exactly once in Earth's history, from a single unlikely merger of two simpler organisms. That transition took over 1 billion years and may have been the closest thing to a lottery win in the history of biology. If these early steps, the origin of life, the emergence of complex cells, are the filter, then we have extraordinarily good news. We've already passed it. Simple life may be common throughout the galaxy, but in the vast majority of cases, it never gets further than bacteria. We, through some improbable chain of events, broke free. In that case, the silence isn't a warning. It's evidence that we're rare and possibly free to expand. The second possibility, the filter is ahead of us. This is a scenario that gives serious scientists pause. What if life is actually fairly common? What if complex organisms, intelligence, technology, all of that is achievable, maybe even predictable? And what if the thing that almost nothing survives is what comes next? The transition from a technologically capable civilization to one that endures. Consider the evidence from our own species. We went from the first powered aircraft to nuclear weapons in 40 years. From the discovery of the double helix to CRISPR gene editing in about 60. We now have artificial intelligence systems advancing faster than our regulatory frameworks can track. Each of these technologies represents enormous potential and also the possibility of catastrophic misuse, accident, or unintended consequence. A 2024 study in Science Progress raised the uncomfortable possibility that intelligent species may be, in a sense, genetically wired for short-term thinking, that the behavioral patterns shaped by millions of years of evolutionary pressure are fundamentally incompatible with the kind of long-term coordination required to navigate existential risks. Not because we're evil, because we're human, and humanity evolved to solve problems that were immediate, local, and visible, not slow-moving, diffuse, and global. If that a general pattern, if every species that reaches technological capability carries with it the instincts and cognitive biases that made it competitive in a biological world, but make it dangerous in a technological one, then the great filter ahead isn't one catastrophic event. It's a developmental phase that almost nothing survives. And here's what makes this genuinely disturbing. If the filter is ahead of us, then the more we find life elsewhere in the universe, the worse the news. Every bacterium discovered on Mars, every biosignature detected on a distant exoplanet, is not cause for celebration. It's evidence that life gets started easily, that the early steps are not the filter, and that whatever is killing civilizations is something that happens later, something we haven't faced yet. But then there's a third possibility, one that isn't really about probability at all, one that doesn't ask can civilizations survive, but would they choose to make themselves known? This is a theory that has perhaps gained the most cultural traction in the last decade. It comes not from a scientific paper, but from a novel, and yet it encodes a logic that a number of serious researchers have found genuinely difficult to dismiss. It's called the dark forest. The concept was developed by Chinese science fiction writer Liu Cixin in his trilogy, The Three-Body Problem. Specifically in the second book, The Dark Forest, published in 2008, and it runs like this. The universe operates on two fundamental axioms. First, every civilization's primary drive is survival. Second, resources are finite and cannot be perfectly shared. From these two premises, a brutal conclusion follows. Any civilization that detects another faces a fundamental uncertainty. It cannot know the other civilization's intentions, and it cannot know how quickly that civilization will develop. Even if it seems harmless now, it might not be in 1,000 years, and by then it may be too late to act. The only rational strategy, if you accept these premises, is preemptive elimination, not out of malice, out of logic. In a universe where this is true, every civilization that wants to survive learns, eventually, to hide, to stay silent, to erase any trace of its existence. And any civilization that broadcasts its location, that shouts into the dark, doesn't do so for long. This, Liu argues, is why the forest is silent, not because it's empty, because everything in it has learned to be very, very quiet. It's a compelling framework, and it has real critics. Some researchers point out that it assumes a particular kind of game theory that may not apply universally to all possible forms of intelligence. It assumes scarcity of resources in a universe where stars are burning energy for billions of years. It assumes that civilizations remain recognizably self-interested in the way biological organisms are, even after potentially millions of years of development. Others note a simpler logical problem. If the dark forest is real and every civilization hides, who exactly is doing the hunting? A universe of hunters who never reveal themselves looks, from the outside, exactly like a universe with no hunters at all. The theory predicts silence, but so does emptiness. What the dark forest does usefully, regardless of whether it's literally true, is force a question we haven't seriously confronted as a civilization. We have been broadcasting our existence for over a century. We have sent physical messages into interstellar space. We've beamed targeted signals at specific stars. We've done this without global debate, without scientific consensus, and without any plan for what we do next if something answers. If the universe contains even one civilization that behaves the way the dark forest theory predicts, we may have already made a mistake we cannot take back. Or perhaps not. Perhaps the universe is more complex, more varied, more strange than any single theory can hold. Perhaps there are 100 answers to Fermi's question, each true in a different corner of the cosmos, none of them applicable to all of it. But here is what we can say with certainty, standing where we stand right now, with the instruments we have and the silence we keep receiving. We don't know, and in the space of that not knowing, every answer carries its own weight of consequence. On February 4th, 2008, NASA pointed a 70-meter antenna at the North Star and pressed play. The song was Across the Universe by the Beatles. Polaris is 431 light years away. The signal won't arrive until the year 2439, long after everyone involved in the decision is dead, long after the civilization that made it may look entirely unrecognizable. Nobody asked permission. Nobody voted. A handful of people at a space agency decided, in celebration of their organization's anniversary, to broadcast a piece of human culture to a point in the galaxy and call a milestone. It was a beautiful gesture. It was also, quietly, a profound illustration of a problem nobody likes to look at directly. We have been announcing our presence to the universe for over a century, not intentionally at first. Every radar pulse, every television transmission, every radio signal since the early 20th century has been expanding outward from Earth as a growing sphere of electromagnetic noise. We didn't choose to send it. It was a byproduct of being alive in the modern world. But then we started doing it on purpose. In November 1974, the Arecibo Observatory in Puerto Rico, at the time the largest radio telescope on Earth, was used to transmit a focused, binary-encoded message toward Messier 13, a globular star cluster in the constellation Hercules. The message was 1,679 bits long. Arranged correctly, it depicted a human figure, our solar system, the structure of DNA, the numbers 1 through 10, and the atomic numbers of the elements that make up life as we know it. It took less than 3 minutes to transmit. Messier 13 is roughly 22,000 light years away. A reply, if one ever came, would arrive in 44,000 years. The people who sent it knew this. That's worth sitting with. They transmitted a message with a certain knowledge that no one alive would ever hear an answer. Not them, not their children, not their civilization as it currently exists. It was a message in a bottle thrown into an ocean so vast that waiting for a response becomes almost a philosophical concept rather than a practical one. The reaction from the scientific community was not uniformly celebratory. Martin Ryle, British astronomer, Nobel laureate, one of the founders of modern radio astronomy, objected immediately. Broadcasting Earth's location, he argued, was reckless. We had just told anything listening, exactly where to find us, what we look like, and how our biology is structured. We had done this without any global discussion, without any democratic process, without any consensus whatsoever. A few scientists had spoken for 8 billion people, for every person alive, for every person who had ever lived. That objection was largely set aside at the time. It has not gone away. The practice now has a name, METI, Messaging Extraterrestrial Intelligence, and the debate surrounding it has grown considerably more serious in recent decades. In 2015, a group of researchers, spanning astrophysics, biology, anthropology, and public policy, signed an open letter calling for a moratorium on METI transmissions until an international framework for consent and decision-making could be established. Their argument was straightforward. The potential consequences of contact are global and permanent. The decision to initiate it should not rest with individuals or organizations acting unilaterally. The counter-argument is equally straightforward. It's too late. Our radio bubble has been leaking into space for 100 years. Any civilization within that range that has technology comparable to ours already knows we're here. The Arecibo message was a focus beam. The background noise of human civilization, television signals, military radar, satellite communications, has been propagating outward for generations. We cannot unring that bell. Both sides have a point. That's what makes this genuinely uncomfortable. Meanwhile, the Voyager probes, launched in 1977, now the most distant human-made objects in existence, both having crossed into interstellar space, carry something more intimate than a radio signal. Each spacecraft carries a golden record, a gold-plated copper disc encoded with 115 images, sounds from Earth's natural world, spoken greetings in 55 languages, and 90 minutes of music from cultures across the world. Chuck Berry, Beethoven, Azerbaijani folk songs, the sound of wind, rain, and surf, a mother's first words to a newborn child. The Beatles wanted to be on it. The song they proposed was Here Comes the Sun. EMI, which owned the copyright, said no. The asking price was too high. And so the most ambitious physical message humanity has ever sent into interstellar space went out without the Beatles, because a record label was concerned about licensing fees. The Voyager probes travel at roughly 35,000 miles per hour. At that speed, it will take approximately 40,000 years to reach the nearest star system. Nobody will be there to meet them. And this is where the question underneath all of this finally surfaces. The question that tends to get buried beneath technical details and probability calculations. Who speaks for Earth? Not rhetorically, literally. When we encode our biology, our location, our culture, and broadcast it into the cosmos, we are making a claim of representation. We are saying, this is who we are. This is where we are. Come find us if you want. No vote was taken. No global consent was gathered. The people who sent the Arecibo message were brilliant, well-intentioned scientists operating within the norms of their field. So were the people at NASA who chose to beam a Beatles song to Polaris. So is a team at NASA's Jet Propulsion Laboratory that has since proposed a new interstellar transmission, the Beacon in the Galaxy, intended for eventual broadcast using the world's most powerful radio telescopes, designed to be a comprehensive, updated introduction to humanity to whatever might be listening. Each of these decisions was made by a small number of people, acting on behalf of a species that was never asked. This is not an accusation. It may not even be a solvable problem. There is no mechanism by which 8 billion people, speaking hundreds of languages, holding radically different values, disagreeing about almost everything, can reach a unified position on whether to announce their existence to the cosmos. The logistics are impossible. The timeline doesn't permit it. But the impossibility of the process doesn't dissolve the underlying question. It just means the question gets answered by default, by action, by whoever happens to have a large enough antenna and the will to use it. We don't know what's out there. We have been broadcasting for a century, and somewhere in the arithmetic of the Fermi Paradox, that fact sits quietly and waits Everything we've discussed so far is operated on a single, mostly unstated assumption that civilizations, when they exist, are detectable, that intelligence, when it develops, expands outward, that a species advanced enough to reshape its stellar neighborhood would do so in a way we'd recognize, or at the very least, in a way that leaves traces we know how to look for. That assumption may be where the whole framework breaks down. Consider what has happened in a single human lifetime. In 1950, the same year Fermi asked this question over lunch, a computer was a room-sized machine that could perform basic arithmetic and required a team of engineers to operate. Today, billions of people carry devices in their pockets that contain more processing power than the entire computational infrastructure of that era. The trajectory of this progression, if extended even a few hundred years, becomes almost impossible to reason about from where we stand. A civilization 1,000 years more advanced than ours is not just us with better rockets. A civilization 1,000,000 years more advanced may have undergone transformations so fundamental that the categories we use to describe intelligence, expansion, communication, and even physical existence simply don't apply to them anymore. This is what researchers sometimes call the problem of post-biological civilizations, and offers a class of explanations for the Fermi Paradox that requires no catastrophe, no cosmic filter, no sinister silence. It requires only that we are thinking too small, that we are searching for a version of ourselves projected onto the stars, and missing everything that doesn't look like that. The most formally rigorous version of this argument was published in 2003 by philosopher Nick Bostrom. In a paper called "Are You Living in a Computer Simulation?" The argument is technical in structure, but stark in its implications. Bostrom's reasoning runs as follows. If a civilization survives long enough, it will eventually develop the computational capacity to run detailed simulations of minds. Simulations that are, from inside, indistinguishable from lived experience. If even a modest number of such simulations are run, the simulated minds will vastly outnumber the biological ones. And therefore, any randomly chosen conscious entity, you, reading this, watching this, is statistically far more likely to be a simulated mind than a biological one. Bostrom himself is careful. He frames this not as a conclusion, but as a trilemma. One of three propositions must be true. Almost no civilization ever reaches a stage of running such simulations. Almost all civilizations that reach that stage choose not to run them, or we are almost certainly living in one right now. He doesn't tell you which is true. The logic doesn't allow for that. What it does is force a confrontation with a possibility that is genuinely difficult to dismiss with current tools. If the third option is true, if we are in a simulation, the Fermi paradox dissolves. We don't see other civilizations because we're not looking at the base universe from the outside. We're inside a construct that doesn't need to populate itself with a visible galactic community to serve its purpose. The silence is an absence. It's architecture. This may sound like science fiction. Philosophers and physicists who have engaged with it seriously would tell you it is not obviously false. But the simulation hypothesis is just one member of a broader family of explanations. What they share is a concept of transcendence, the idea that advanced civilizations don't expand outward the way we imagine. They go inward. There's a concept proposed by researcher John Smart called the transcension hypothesis. It suggests that the developmental arc of advanced civilizations is not toward larger structures, not Dyson spheres and galaxy-spanning empires, but toward increasingly dense, efficient, miniaturized substrates. Smaller, not larger. Deeper, not wider. More internal, not more visible. A civilization far enough along that trajectory would be undetectable not because it's hiding, but because it has moved somewhere we don't know how to look. It would have left the observable universe in the only way that matters. It would have made itself irrelevant to the frequencies and scales we monitor. There's also a possibility raised by researchers thinking about artificial general intelligence and its long-term successors, that biological intelligence is simply a transitional phase, a brief, combustible stage between the emergence of organic thought and the far longer dominion of machine intelligence. And what comes after may be so different in its architecture, its interests, and its timescales that it has no reason to broadcast, colonize, or signal in any form we would recognize. Not hostile, not hiding, just elsewhere in every meaningful sense. This class of explanations is disorienting in a particular way. It doesn't just answer the paradox. It changes the question. We've been asking, where is everyone? Maybe the more accurate question is, what has everyone become? The silence of the cosmos might not be the silence of emptiness. It might be the silence of something so far beyond our current form, so different in its nature, its timescale, its concerns, that our attempts to detect are like an insect trying to detect a symphony. Not because the symphony isn't playing, because the insect doesn't have the apparatus to hear it. None of this is straightforwardly comforting. The simulation hypothesis raises questions about the nature of existence that philosophy, religion, and science are not currently equipped to resolve. The transcension hypothesis, if true, suggests that the long arc of all intelligence bends toward a kind of radical interiority, a turning away from the shared universe, which carries its own particular loneliness. And the post-biological possibility implies that the endpoint of intelligence is not connection. It's transformation into something that no longer needs to reach out. But what these ideas share, and why they matter for the question Fermi asked, is this: they suggest the silence might not be a wound. It might be an answer, not the answer we were looking for, not one that resolves the paradox cleanly or hands us a map of the galaxy's inhabited worlds, but an answer that reframes the terms entirely. Maybe we're not alone in an empty universe. Maybe we're alone in the part of the universe we know how to see. Let's go back to the beginning. A summer afternoon in 1950, a group of physicists eating lunch. A question so simple, it almost didn't sound like a question. Where is everybody? We spent an hour and, in a deeper sense, the last 75 years, trying to answer it. We built telescopes powerful enough to detect the chemistry of atmospheres on planets 124 light-years away. We've cataloged hundreds of billions of stars and confirmed that most of them have worlds. We've listened on every frequency we know how to use, and we've sent our own voice out into the dark, and we've waited. We've developed theories rigorous enough for peer-reviewed journals and disturbing enough to reshape how certain researchers think about the future of our species. We've traced the evolution of life on Earth down to the molecular level and used it to argue, simultaneously, that we are a near-miraculous accident and that the galaxy should be crowded with civilizations like ours. We've thought carefully about catastrophe, about transcendence, about the possibility that the universe as we experience it is a layer over something we can't access. And we have not found an answer. What we found is something different, that the silence carries meaning, that it's not a blank space waiting to be filled. It's a mirror, and depending on how you look into it, what you see changes. There are three ways to read what the silence is telling us. The first reading, the silence is a warning. If the great filter is ahead of us, if the transition from technological civilization to enduring civilization is a threshold that almost nothing survives, then what we're hearing in the cosmos is an involuntary archive of failure, not monuments, absences. Every star system that might have harbored a civilization is now a memorial to what happens when intelligence becomes powerful faster than it becomes wise. This reading says, the silence is a statistical residue of species that got exactly where we are and did not make it through what comes next. It is a message encoded not in signal but in absence. And its meaning, if you accept this interpretation, is unambiguous. We are approaching something. The silence on the other side of it is total. It asks us to consider whether a species that evolved to solve immediate, local, visible problems, food, predators, rivals, is equipped to navigate threats that are slow-moving, diffuse, and global. Whether the cognitive architecture that made us competitive over hundreds of thousands of years of biological evolution is compatible with the kind of long-horizon thinking required to survive the next 100. The warning doesn't tell us we'll fail. It tells us that almost everything does, and that knowing this might be the only edge we have. The second reading, the silence is hope. If the great filter is behind us, if the almost impossibly specific chain of accidents that produce complex life on Earth is a hard part, the nearly insurmountable part, then the silence is, paradoxically, the best news we could receive. It means we made it through the bottleneck. It means the universe is not saturated with civilizations that have had millions of years to develop and expand and overwhelm everything that came after them. It means that intelligence, whatever that word really means, is extraordinarily rare, and that we may be among the first instances of it to reach this particular threshold. To be first is not a comfortable position. There is no precedent, no guide, no signal from ahead telling you that the path continues, but also means something remarkable. If intelligence is going to persist, if something that wonders and builds and asks unanswerable questions is going to endure across cosmic time, then what we do with the civilization we have is not just our concern. It may be the only opportunity the universe has ever produced for this particular experiment to continue. Not because we're special in some cosmic sense, because we're here and almost nothing else is. The third reading, the silence, is a responsibility we haven't yet earned. This one is harder to hold. We don't know what the silence means. We have frameworks and hypotheses and probability estimates. But the fundamental question, are we alone, remains unanswered. We have been listening for 65 years with instruments that are, by any reasonable cosmic standard, primitive. We have covered 1,000th of our galaxy's diameter with our electromagnetic voice. We have examined a fraction of the potentially habitable worlds in the observable universe. What we have is not an absence of evidence. It is insufficient evidence. Those are not the same thing. And in the meantime, while the evidence remains insufficient, we are making decisions. We are broadcasting. We are building technologies that will reshape what it means to be human, and possibly what it means to be intelligent at all. We are doing this without any shared framework for what it means to be a young civilization in a universe that may or may not contain others, that may or may not be observing, that may or may not care. This reading doesn't ask whether the universe is dangerous or benign. It asks something closer to home. It asks whether we are, whether a species that has existed in its current form for roughly 300,000 years and has been technologically capable for about 200 of them, is capable of the kind of thinking that distinguishes a civilization that earns its future from one that doesn't. The silence in this reading is not about them. It has always been about us. In August 2025, the most detailed analysis ever conducted on the WOW, Signal concluded once again that it cannot be explained. It may be natural. It may not be. The data is not sufficient to decide, and the researchers themselves said so plainly. In April 2025, the most powerful space telescope ever built found what might be the chemical signature of biological processes on a world 124 light-years from Earth. It might be life. It might be chemistry. The signal sits below the threshold of scientific certainty, and the scientific community remains divided. The James Webb Space Telescope continues to observe. Ground-based arrays continue to listen. A new generation of instruments is being designed that will extend our reach further and with more sensitivity than anything that has come before. Every year, the search becomes more sophisticated. Every year, the silence holds. The universe is 13.8 billion years old. We have been listening for 65. There are stars in this galaxy that formed and burned out entirely before our sun existed. There are worlds that have had billions of years more than us to develop. Whatever comes after biology, whatever comes after civilization, whatever comes after the kind of questions we even know how to ask. And from all of it, from every direction, across every frequency, across the entire span of our search, nothing has come back. No signal, no artifact, no evidence that the question was ever heard. Just a universe doing what it's always done, existing without explanation, without acknowledgement, without reply. Fermi put down his fork and asked for words. We built satellites and telescopes and listening arrays that span continents. We encoded our biology in binary and sent it to the stars. We attached gold records to spacecraft and let them drift into the dark between solar systems. We looked. In every way we knew how to look, we looked, and the question is still there. Unchanged, unanswered. Where's everybody?